So this is our lesson video for section 5.1. This is one of my favorite chapters. Of course, they're like all my favorite chapters. But we are going to get into focusing on the electrons of atoms and ions. So first, let's kind of continue. From chapter 4, we started talking about the history of how we discovered what atoms look like when we can't actually see them. So the Rutherford's model of the atom did not explain how an atom can emit light or the chemical properties of an atom. So if you remember back in chapter 4, we discussed the plum pudding model, where they thought that you had kind of this big positive force-filled area with electrons thrown throughout. And then, of course, Rutherford did his experiment with the gold foil and determined that was not accurate. So then Rutherford came up with his model where you have your nucleus in the center and your electrons are just kind of somewhere around the nucleus. But again, it didn't give the explanation for how the atoms work in reactions and how come we can electrify a gas and it emits light of different colors. So they did some more experiments. So Niels Bohr, he studied the hydrogen atom because it was the most simplistic. Hydrogen atoms have one proton, one electron, and a lot of times 0 neutrons. They can have a neutron or two depending on, of course, what isotope you're looking at. So Bohr proposed that an electron is found only in specific circular paths or orbits around the nucleus. So whereas Rutherford just knew they were somewhere around the nucleus, Niels Bohr kind of put it more like a planet system where you have an orbit, but just keep in mind the orbit doesn't have to only stay here. It is 3D space. Each possible electron orbit in Bohr's model has a fixed energy, and the fixed energy an electron can have are called energy levels. So he determined that, electrons can exist right here in the first energy level, in the second, and the third, but they can't just exist in the middle or outside of one of the energy levels. And keep in mind that this is all 3D space. Like that's why sometimes it's called an electron shell. It's kind of a 3D type orbiting path. So the energy levels get closer together as you move farther from the nucleus, and the energy levels also get higher in energy as you move further from the nucleus. So in other words, it's kind of like a ladder. Like you start at the bottom, you don't have a lot of potential energy, and as you go up each step, you start gaining more and more potential energy because you're getting higher from the ground. Well, it's different than a ladder in the fact that where a ladder, the steps are equally spaced, and the energy levels, they're spaced further apart when you're near the nucleus, and as you get further, they get closer together. That becomes important when we start talking about electron configuration. Okay, so here's the nucleus. First energy level has lowest energy. Second energy level is higher, third's higher, so forth and so on. And as you get further away, notice they get closer and closer together. So electrons can jump from one energy level to another. So a quantum of energy is the amount of energy required to move an electron from one energy level to another. So even though an electron may be in energy level 1, if it can gain a certain amount of energy known as a quantum, then it can actually jump to the second energy level. But it has to be in 1 or 2. Like it's not like it can jump halfway into a half energy level. So Bohr really gave us 2 completely new ideas, and that is energy levels and that electrons can jump to different energy levels. So an electron must gain energy to jump up to a higher energy level. When an electron has jumped to a higher energy level, it's called excited. An electron must lose energy to fall to a lower energy level. And when an electron is at its lowest energy level possible, it is at ground state. Now, a lot of people confuse that and think, well, ground state must always be energy level 1. Well, we haven't talked electron configuration in here yet, but I'm sure you remember in physical science where you would talk about the first energy level can hold 2 electrons, and then you draw another ring when you do Bohr's model. It's just the lowest energy level possible for that electron. So one electron, the lowest energy level it could go into might be energy level 3. So ground state does not necessarily mean energy level 1. It just means the lowest energy level for that specific electron. So Bohr's model accurately describes the movement of an electron in a hydrogen atom, but it cannot describe the movement of multi-electron atoms. So the unfortunate thing is he did all his studying pretty much on hydrogen, which only has 1 electron. Once you have more than 1 electron, they have to interact with one another. And as you hopefully already know, electrons repel one another because they're negative, and 2 negatives will repel one another. So he was very, very accurate for hydrogen only, but we can take some of what he taught us to apply it to other elements with more than one electron. But we still needed something a little better. So that moves us to the quantum mechanical model. And the quantum mechanical model of an atom is based on the mathematical probability of the location of electrons using the Schrödinger equation. Don't worry, we're not going to start going into calculus in this class. We're not going to do the calculations of Schrödinger's equation. If you move on in college or something in certain chemistry classes that are upper level, you may get to do some of this. I got to do some of it. So anyway, the quantum mechanical model still has energy levels, but the exact path or orbit of the electron is unknown. So the thing to remember when I start showing you all these really weird shapes that you're about to see is it's based on a mathematical equation. It's a mathematical probability of where we'll find the electron. So when you start seeing really weird shapes, just know this was a mathematical calculation. It wasn't just somebody drawing pretty shapes and pretending like that's where the electrons are. This is all based on science and math. So since the quantum mechanical model is based on the probability of finding an electron, then the orbitals are normally shaded with fuzzy edges. So if you look, it's just kind of a series of dots, and you have your nucleus in the middle, and you have a darker or a more dense area of dots around the nucleus, and as you go out, there's less and less dots, and it eventually fades. So an atomic orbital is a region of space in which there's a high probability of finding an electron. So if you look kind of around this area, there's a pretty high probability without those little outliers. Within the border, because we do have to have a border eventually, like we can't just draw this every time. Within the border of an atomic orbital, there's a 90% chance of finding an electron. So what they do is they find where 90% of the dots are, and that's where they'll put the edge of the atomic orbital. The darker the shading, the higher the chance of finding the electrons. If you notice, it's more likely you're going to find the electron the closer you are to the nucleus, and that's of course because electrons and protons attract one another. So these are the four models that we have learned. If you're in my class, you need to make sure to be able to label and draw these on your test. So plum pudding model is a large positive force-filled area with negative electrons throughout. And when I say label, I want you to make sure you're labeling the positives and negatives. Don't just draw a bunch of circles. And you label it's called plum pudding model. Rutherford's model, you have your nucleus, which is positive in the center, and you have electrons just somewhere around it. Okay, you don't even have to draw it this specific, but most people, they associate Rutherford's model with the Jimmy Neutron model. Y'all know what I mean. All right, Bohr's model, you have your positive nucleus in the center. You have specific circular orbiting paths that the electrons can be on. And so you need to make sure, I know this is super tiny, so you probably can't see it. This is a tiny circle with a negative in it. You gotta label those electrons. And then you just need to put an arrow somewhere to show me it can jump from one energy level to another. And the last one's quantum mechanical model. So you have a positive nucleus in the center. And then I usually just draw a circle around it and then just shade it a little bit. So I make it darkest near the nucleus and it kind of fades as I go out. Don't worry, I'm not an artist, so I don't care if you are. Just, try to show me some shading. And then you need to let me know that there's a 90% chance of finding an electron within the border of your orbital. So let's talk a little bit more about these energy levels. So each energy level can be composed of multiple sublevels. So energy levels are assigned a number from 1 to 7 based on the row of the periodic table. So if you look at your periodic table, there are 7 rows or 7 periods, and there are 7 energy levels. So each sublevel can be composed of multiple orbitals, and the sublevels are assigned letters, S, P, D, F, or G. Each orbital can hold a maximum of 2 electrons. So this is going to get confusing for just a few minutes in this video, but just bear with me. Okay, it's all going to come together. We just got to get through this kind of confusing part. All right, so let's look at what the sublevels look like, how many electrons can they hold, and things like that. So all S sublevels have 1 orbital and can hold a maximum of 2 electrons. The number in front of S represents the energy level. So as energy level increases, the size of the S sublevel increases, but it can still only hold 2 electrons. So you're going to see 1s through 7s because there's 7 rows on the periodic table. So there's 7 S sublevels. So they happen to be the shape of a sphere. The S sublevel has a spherical shape. So 1s might be about this size, and it can hold 2 electrons. 2s is still going to be the same shape, so it's still a sphere. Even though it's bigger, because it's still an S sublevel, it can still only hold 2 electrons. A lot of people want to say, oh, well, if one s can hold 2, 2s can hold 4. It doesn't work that way. It's still s, it just means those 2 electrons can be farther from the nucleus. And so then 3s is going to be even bigger, but because it's still s, it still only holds 2 electrons. They're just farther from the nucleus. 4s would get bigger, 5s would get bigger, so forth and so on. Okay, so the number in front does not affect how many electrons it can hold. The electrons are based on the letter. The number in front tells us where we are on the periodic table, which row we're on, and then it tells us the relative size. Like I know 7s is going to be larger than 2s, but they would still both hold 2 electrons. So let's move on to p. All p sublevels have 3 orbitals and can hold a maximum of 6 electrons. Each orbital can hold 2 electrons. So if I have 3 orbitals, 3 times 2 is 6. The p sublevel has a dumbbell or teardrop shape. Each teardrop is referred to as a lobe. So they all exist together. This is taken the 3 orbitals and showing them separately, but notice they all overlap in real life. Okay, so here's what one looks like, here's the second one, and here's the third one. And so when they all overlap, a p sublevel looks like this. Because there's 3 orbitals, it can hold 2, 4, 6 electrons. All right, so let's move on to D. Now, the shapes start getting kind of weird, but remember, y'all, it's based on mathematical calculation using Schrodinger's equation. All right, so all D sublevels have 5 orbitals. So remember, each orbital can hold 2 electrons, so 2, 4, 6, 8, 10. So D sublevels can hold up to 10 electrons. The D sublevel has the shape of like a 4-leaf clover. So if you look, there's 4 lobes, and they're just all in different directions. Now remember, in reality, all of these would overlap, so that's why it's really hard to draw these. So when I show you how to do electron configuration, we aren't drawing pictures. We're going to list numbers and letters, so it makes it a little easier. So you'll either see like the 4 lobes, which is kind of like a 4-leaf clover, or you'll see 2 lobes with kind of a donut around the middle. Okay, so maybe you can remember D for donut. So hopefully you're noticing a pattern. S has 1 orbital, can hold 2 electrons. P has 3 orbitals and can hold 6 electrons. D has 5 orbitals and can hold 10 electrons. So F has 7 orbitals and can hold a maximum of 14 electrons. So again, these are all mathematically calculated. All 7 of these would overlap, making it impossible to draw. But this is just showing them separately what they look like. I don't expect you to know the shape of F. And then G has 9 orbitals, so of course each one can hold 2 electrons, so it can hold up to 18 electrons. Now there are not enough elements on our periodic table to fill in the G sublevels yet. So you may wonder, well then how do they know what they're going to look like? Well remember, they're based on a mathematical calculation. So like for example, I could do a mathematical calculation of a budget if I made $1 million a year, but that doesn't mean I actually make that much. But I can still mathematically calculate what it would be like if I did it. I could calculate, how much extra money would I have and things like that. So it's a mathematical calculation. So if you ever get to when you're doing electron configuration where you feel like you should be filling in G, we're not there yet. Okay, so we won't fill it in. I just want you to know that it does have 9 orbitals and can hold 18 electrons. So this is just a chart. So what I want you to notice is the number of orbitals, it just increases by odd numbers. So 1, 3, 5, 7, 9. And then remember, to get to the number of electrons, you just multiply it by 2. So 1 times 2 is 2, 3 times 2 is 6, 5 times 2 is 10, 7 times 2 is 14, and 9 times 2 is 18. So really you just need to remember the order S, P, D, F, G. So a lot of my students, like in class, I'll make up an acronym with them to help them kind of remember the order S, P, D, F, G. So maybe try to think of an acronym on your own. You're more likely to remember one that you come up with than one we come up with in class. All right, so why did Rutherford's atomic model need to be replaced? Well, it didn't explain how atoms emit light or the chemical properties that an atom has in reaction. All right, so number 2, what was the basic new proposal in the Bohr's model of the atom? Well, I really think there's 2, so I always say 2 in class, and that is energy levels and that the electrons can jump. Okay, so he came up with that idea of energy levels and that electrons can jump. So number 3, what does the quantum mechanical model determine about electrons and atoms? Remember, it's the mathematical probability of finding the electron. Okay, so it shows us the mathematical probability of finding an electron. So number 4, how do 2 sublevels of the same principal energy level differ from one another? Okay, well the sublevels, this is where it takes a little bit of getting used to. The energy levels are 1 through 7. The sublevels are the s, p, d, f, g. The orbitals we'll talk about a little bit later. Okay, so the sublevels are the letters. So in other words, how would S and P differ from one another? Well, there's a bunch of different ways. You could say they have different shapes. You can say they have different numbers of orbitals. You could say they hold different numbers of electrons. That's 3 differences right there, and it only asks for 1 technically. Okay, so they differ in shape, differ in number of orbitals, and differ in number of electrons that they can hold. All right, so number 5, how can electrons in an atom move from one energy level to another? Now notice it didn't say jump up or fall down. So to move, in general, it needs to either gain or lose energy. Okay, so since it didn't specify if it's jumping up or falling down, we need to say it can gain or lose energy. You may wonder, where does that energy come from? Well, it can come from lots of different places. You can heat it, you could pass electricity through it, you could put it through a chemical reaction. There's lots of ways that atoms can gain or lose electricity, gain or lose energy. All right, so it says how many orbitals are in each of the following sublevels. So remember, the orbitals are only based on the letter, not the number. So 3p, p has 3 orbitals. 2s, s has 1 orbital. 4p, it doesn't matter. The difference in 3p and 4p is 3p is the 3rd energy level, 4p is the 4th energy level. 4p is bigger in space, but it still has the same amount of orbitals. 3 orbitals and can still hold 6 electrons. 3d, d has 5 orbitals, and 4f, f has 7 orbitals. Okay, so the orbitals and number of electrons are based on the letter, not the number in front. All right, so if you're still a little confused, that is completely normal. You really need to get into section 5.2 before it kind of all starts coming together. But trust me, if you'll just hold on and hang in there, everyone pretty much thinks the electron configuration is super easy. So you just got to give it a chance.